Okay, so good morning children. Welcome to the next physics chapter. We have sound lined up for you. It's quite a big chapter, so you'll have to have a number of lectures for it. We'll just see how many lectures it takes. Let us first begin with the very basics of sound. Now, what do you understand by sound? Sound, we all know, it is a sensation that our ears have. Okay, now there are a number of things that you have to understand about sound. First is, what is sound, how is it produced? Okay, so if you read the first line over here, it is a form of energy, just like light energy. Light is a form of energy. So we have the hydroelectric energy, we have electrical energy, we have solar energy, we have similarly we have the sound energy. Okay, so it is a form of energy which travels in the form of waves. Okay, so a form of energy traveling in the form of waves. Okay, so sound is a form of energy. That is the first thing that we understand about sound. Now, how is it produced, or how is a sound created? Like, for example, if I am speaking, you can hear me. Okay, so what is the thing that is producing this sound that is coming out of my mouth? So it is some vibrating body. Okay, so if you read the second line, it is caused by vibrations or a vibrating body. So in the case of myself speaking to you, what is that vibrating body? It is the vocal cord in my mouth. It is the vocal cord that is vibrating and that is creating sound or generating sound. Okay, so number one, for sound creation, there has to be something that has to vibrate. Okay, so the presence of a vibrating body is essential for the generation of sound. Okay, and please remember, sound is nothing but an energy waveform. Okay, so come to the third point. It travels with the help of particles of the medium. Okay, so again, coming back to the same example, I am speaking and you are able to hear me. Okay, so the first thing that my vocal cord is doing is my vocal cord is vibrating. That is why the sound has been generated. Okay, it has only been generated, number one. Now, for you to be able to hear the sound that is generated, it has to travel from my mouth to your ears. Okay, so that traveling portion is responsible, because that traveling portion is taken into account with the help of the medium. Now, in this particular case, the medium is air. Okay, or the gaseous medium. Okay, so now there are two things that we understand about sound. Number one, its generation. How is it generated? It is generated because of a vibrating body. Number two, how does it travel? It travels with the help of the particles of the medium. So a medium is absolutely necessary for the sound to travel from one place to another. Okay, so for the sound to travel from my mouth to your ears, it is absolutely necessary that there must be a medium present between the two things, the source and the listener. Okay, so this medium obviously can be a gaseous medium, it can be a solid medium, it can be a liquid medium, does not vary. Actually, it depends upon the different mediums, but then in all mediums, sound will travel. Okay, suppose we take vacuum for example, in which light can travel. We all know, just now we discussed that sound as well as light, they are forms of energy, but there is a very major difference between these two types of energy waves. That is that light can travel through vacuum also, or in other words, light does not require any medium to travel. Okay, whereas sound, it actually travels with the help of the particles of the medium. You have already done this bell jar experiment in class 9th, I think, in which if you take out the entire air from inside the bell jar, then there will be no sound heard, because although the sound is getting generated, but it cannot travel because there is no medium present. Okay, so this was the second thing. Now the third thing that is extremely important again for you to be able to hear what I am speaking is the ability of your ears to perceive that sound. Okay, so there are three things that are important. Number one, generation of sound. Number two, traveling of sound. And number three, the perception or the feeling of that sound when it falls on the cochlea in your ears. Okay, now you see, if you read that last line, requires a medium unlike light waves which do not need any medium to travel. So we have already discussed this part. Light waves actually don't require any medium. They can travel in medium, they can travel without any medium, but sound necessarily requires a medium to travel. Okay, so this is the basic of the sound. Now, sound wave, since it is a wave, if you remember in light waves also we had discussed the formula V is equal to F lambda. That's the general formula for the velocity of any wave. Okay, so you see velocity of wave is represented by this capital V, and F obviously is the frequency of the wave. Now that wave can be a light wave also, it can be a sound wave also. Here it is sound wave. Okay, so this F is the frequency of the sound wave, and again it depends upon the source of the sound or the vibrating body. Okay, so once a sound has been produced, its frequency has been set. Okay, please remember always the velocity and the wavelength of the sound, they are actually related to the medium in which it is traveling. If you read over here, velocity comma wavelength, they depend upon the medium of travel. Okay, so if it is air, the velocity and the wavelength will be different. If it is solid, it will be different. Similarly, in liquids, it will be different. But the frequency of that sound wave will not depend upon the medium, because it depends upon the source of the sound. So once the source has been generated, once the sound has been generated at the source, F value is set. Okay, so the only thing that changes depending upon the medium in which the sound is traveling is your lambda, and therefore your change in lambda creates a change in the velocity of the sound wave. Okay, so for example, you can read over here, I have listed some examples. For example, gas, liquids and solids. Sound can travel obviously in all the mediums. You can see velocity of sound is the lowest in gaseous medium, then in liquids it is slightly more, and then in solids it is the highest. Okay, so this is the order in which the velocity of sound varies. Okay, and there are some examples taking up the values. If you see example in air, the velocity of sound at around room temperature is somewhere around 330 to 340 meters per second. Okay, whereas if you see in water, around 1200 to 1400 meters per second. So there is a vast increase if you see from the velocity of sound in air to the velocity of sound in liquid, which is water in this case. Similarly, when you go to the solids, for example metals, now these are not the exact values. You may have a look online, you will find that the velocity of sound in most metals, it is much higher than what you have over here in the liquids. Okay, so this value may not be exactly correct, but then it is certainly much more than what you see over here. Okay, so if you see, it is going down in the ascending order, it is increasing, the velocity of sound is increasing in air, then in liquid, then in solids. Okay, so this change in the velocity is because of the change in the medium of travel. Okay, if somebody now asks you, will the frequency of the sound be different in these three cases? No, the frequency of sound will remain the same, because if the source of generation is same, the frequency is same, because frequency of sound wave again depends upon only the source of sound. Okay, now let us come down to the frequency aspect. Just now we understood the velocity and the wavelength aspect of it. Now we are going to understand the frequency aspect. Now frequency also varies. Okay, if you remember in 9th standard, the frequency, amplitude, wavelength, all these things we had studied. So frequency is the number of oscillations in 1 second. Okay, or the number of vibrations taking place in 1 second. More the number of vibrations in 1 second, higher is the frequency. Lesser the number of vibrations in 1 second, lower is the frequency. Okay, so now hertz is the SI unit. Capital H, small z is the SI unit of frequency. If you see, in terms of sound waves, in terms of the frequency of sound waves, there are three classifications given over here. Between 20 Hz to 20,000 Hz, this range of frequency is known as the sonic or the audible range of frequency, and it is this particular frequency range that humans can hear. Okay, so our ears have been designed to perceive or to listen this particular range of sound. So suppose, for example, when I am speaking, you are able to hear me. You are able to hear me. Why? Because the frequency of the sound that is coming out of my mouth is falling in this range, between 20 Hz to 20,000 Hz. That is why you are able to hear what I am speaking. Okay, so please remember, this range is known as the sonic or the audible range, which we humans can hear. Now, supposing sometimes you might have seen that if you have, especially if you have a dog sitting nearby, lying in a sort of a rest position, suddenly you see that the dog becomes very active. Okay, so he must have heard something. Now, you as a human have not heard anything, but that particular animal has heard some particular frequency of sound, and that is why he suddenly becomes active. Okay, so now you are wondering, what is it that he has heard that you cannot hear? That particular difference is because of the frequency of the sound. Now he may have heard anything, let's say for example, maybe a frequency of sound which is not falling in this 20 to 20,000 range. That is why you are not able to hear it, but the dog could hear it. Okay, so above 20,000 Hz, if the frequency of the sound is above 20,000 Hz, it is known as the ultrasonic sound. Obviously humans can't hear it. Similarly, if you go to this range below 20 Hz, then the sound is known as infrasonic sound. Again, all these three are sounds only. Does not matter whether you can hear them or not. You can only hear the first one, you cannot hear the remaining two. That does not mean that the remaining two are not sound waves. They are all are sound waves. Some you can hear, some you won't, depending upon this particular range. Now, as you can see, I have listed over here ultrasonic as well as infrasonic sounds. They can be heard by different categories of animals. For example, if you read the book, in the book you will find out that there are some animals like bats, dolphins, etc. that are responsive to the ultrasonic waves, whereas the heavier animals, for example, let's say elephant or some other heavy animals, if you read, they can actually detect infrasonic sounds as well. Okay, so if you read the book, you will get a better idea of the frequency classification. So if you see, these are this you can call this as the frequency classification, the classification of sound waves based on the frequency. Now, if somebody asks you, in air, what will be the velocity of sonic waves, what will be the velocity of ultrasonic, what will be the velocity of infrasonic waves? Remember, the medium given is air in all these cases. Okay, so obviously the velocity of sound will be the same, whether it is an ultrasonic wave, whether it is an infrasonic wave, or it is a sonic wave. The velocity, please remember, velocity depends upon the medium of travel. So if the medium is air in all these three cases, the velocity of sound will be same. Whereas you can only hear this sound, you can't hear these two sounds. That is not because of the velocity, that is because of the frequency difference. Okay, so based on the velocity, based on the frequency, you have different classifications of sound waves. Okay, so now let us move ahead. Now we are okay with the basics of sound waves. Now let us go into a little more detail. Now please pay attention, this is not an exactly very easy details that we are going to study now. So sound waves, they are classified into longitudinal waves and transverse waves. Okay, number one, longitudinal waves, they can travel in solids, liquids and in gases. So they can travel in all these three different mediums. Okay, whereas transverse wave, They can travel only in solids and on the surface of liquids. They cannot travel in gaseous mediums. I'll tell you the reason why. Let us first understand what are longitudinal waves. Now here is the diagram that I have drawn. Suppose this is the source of sound, okay? Here is the source of sound. Somebody is speaking over here. Now what happens is the energy that is coming out of the mouth, your vocal cord is vibrating, so it is setting some energy into motion, okay? So that energy, it comes out of the mouth and it forces the nearby particles over here. So now what is the medium present over here? The medium present over here is all air or gaseous medium, okay? So the moment you open your mouth and speak, energy comes out and it hits the immediate particles next to your mouth. So those particles, when they are hit, they move closer to the next particle. So obviously when you hit something, it moves away from you towards the next person, okay? So this way, if you see, there is an area of high density which is created over here. All the particles, most of the particles, they are close together momentarily, okay? So it is like one particle going and hitting the next particle. So momentarily it will be very close to the second particle. So this particular area becomes an area of more density or high density, and this is known as the compression area. Now what happens after that? Remember, this is only a momentary process, okay? First particle goes and hits the next particle. Now that next particle gets into motion, it goes and hits the third particle, okay? So the disturbance that was created at the first particle has traveled to the second and to the third and then to the fourth and so on. So that disturbance starts moving away from the source. Where is the source? This is the source of sound, okay? So now have a look at the very first particle after it hits the second particle. The first particle, after it hits the second particle, it comes back to its original position, okay? Now what happens is, after a little while, the second particle gets into motion and it goes on to hit the third particle, okay? And after hitting the third particle, the second particle also comes back to the rest position or to a position of relative ease, okay? So what is happening over here is, this disturbance which was created right here at the source, it is traveling forward in the form of compressions and rarefactions. Please note the spelling of rarefaction. It is R-A-R-E-F-A-C-T-I-O-N. Rarefaction is just the opposite of compression. It is an area of less density, okay? So when the particle, after hitting, it comes back to its relaxed position, then you see that there is an area of lesser density which is created, okay? So we can easily now say that longitudinal waves are created with the help of areas of compressions and rarefactions. And what is the direction of motion of the particles? Are the particles really getting disturbed? Yes. The source of the sound which is created over here, this is the one that is disturbing the first set of particles, which go on to disturb the second set of particles and so on. So the direction of the sound wave is in this direction. If you can see over here, I have drawn the arrow. This is the direction of wave traveling, okay? Now what is the direction of the particle motion? Are the particles really traveling? No, the particles are not traveling. They are only sending the disturbance forward. How are they sending the disturbance forward? They hit the subsequent particle and then they come back. So the particle which was over here will not travel here. It will remain over here. But it will, in the process, it will disturb the second particle. Second particle will disturb the third particle and so on. Okay. So this way, if you actually realize for a moment, the direction of the particle motion is also in this direction. Also, although it does not really travel the distance, but the disturbance or the vibration is in this direction. Every other particle is hitting the subsequent particle in this direction. Okay, because the source of sound, it directed the energy in this direction. Okay, so when somebody asks you what is longitudinal wave, longitudinal sound wave is a wave in which the direction of particle motion and the direction of the wave is same. It is in the same direction. Please remember, compressions and rarefactions subsequently they take place. Okay, so this is how the wave, longitudinal wave, travels. Okay, this is an example of the way the sound travels when people speak. Okay, now let us come to the transverse waves. Now this is the transverse wave motion. You have already studied this. You see, instead of compressions and rarefactions, here we have crest and trough. C and T. C crest, T is trough. Okay, now here what do you see? You see the direction of wave travel obviously is the same, like in this particular direction, but if you see the direction of particle motion is up and down, up and down. Okay, so it is at an angle of 90 degrees. It is an angle of at an angle of 90 degrees to the direction of wave. So if the wave is traveling in this direction, the particles are oscillating up and below, up and below. Now this is the basic difference between a transverse wave and a longitudinal wave. In a transverse wave, the direction of wave propagation and the direction of particle motion, they are at 90 degree, whereas here you already saw that they were both in the same direction. Okay, now I'll give you an example, a practical example to understand this particular transverse wave motion. Suppose there is a still pond, okay, a pond, talab. Okay, so if you drop silently, if you drop a piece of stone somewhere on the surface of the pond, what do you see? You see there are subsequent waves that are getting generated. You created the disturbance. There was a disturbance when the stone hit the water, a disturbance or a vibrating body set into motion. Okay, so that disturbance, now it is affecting the liquid particle medium. Okay, so what they are going to do is they are going to create a wave motion like this. Okay, so above it is a crest and then down below it is a trough. Okay, so this is the way that the disturbance travels outwards radially. Okay, so suppose that this was the area where you created the disturbance, where you dropped the piece of stone. So all around this there will be waves that will be set, and they will set out like this, radially outwards. Okay, in the transverse wave form. Okay, got that? Now if you really want to check the particle motion, what you can do is you can tear up a very small, very light piece of paper and you drop it on the surface of water. You will see that as the waves move outwards, the piece of paper that you have dropped will not really travel forward with the wave. It will keep moving up and down, up and down, up and down. It may move slightly from its place because wave motion, basically it cannot be an ideal case. There will be other disturbances also. But you will notice very clearly that the small piece of paper that you have dropped, it will keep on oscillating in the near vicinity of the place where you have dropped it. It will not travel with the wave. The wave travels forward, but the particles keep on moving up and down. Okay, so that is the basic difference between the longitudinal and the transverse waves. Okay, now let us quickly come down to the general formula. Now you will have to keep in mind there are different cases of longitudinal and transverse waves involved. Okay, so general formula, if you see general formula for the velocity of sound wave in any medium. Now this is a general formula, so this will apply in all mediums. Velocity is equal to under root E upon D. E is the elasticity of the medium, D is the density of the medium. So obviously both elasticity as well as the density of medium will vary if you change the medium. If you take air, this value will be different. If you take solid, for example, the values will be different. If you take liquids, the values will be different. Now what is important is not really this formula, because this formula, elasticity and rigidity, all these details, they usually come in the higher classes. But what you must understand is this particular formula over here. You see, velocity is equal to under root gamma capital P upon capital D. This is the velocity of longitudinal waves in gaseous medium. Please understand, there will be a number of formulae coming up. All will be for the velocity of sound, but in different situations. As I told you, now here these are two different formulae, but the situation is different. This is a general formula for the velocity of sound wave in any medium. Okay, whereas this is a formula for the velocity of longitudinal waves in particular in gaseous medium. So if you have a solid medium, maybe this formula will not work, because this is the formula for longitudinal waves. Where? In which medium? In gaseous medium. Okay, so obviously P will be the pressure of the gas or the medium that you are taking. D will be the density of the gas or the medium that you are taking. Gamma is a constant. Okay, gamma is the ratio of Cp and Cv. But this detail you will not be studying at this level. You just understand for the time being that the gamma value, gamma is a constant, and that constant will be given to you in case the question is asked. Gamma will be given to you, and gamma will obviously depend upon the gas that we are taking. If it is an oxygen gas, gamma will be different, hydrogen different, and so on and so forth. So gamma is a constant. So now if somebody asks you, what does the velocity of longitudinal sound waves really depend upon in a gaseous medium? So number one, if you see, it depends upon the density of that particular gas or the medium. Now, density of the gas. How will you change the density of the gas? Suppose, I'll give you an example. Suppose you increase the temperature. Okay, suppose you are increasing the temperature of the surrounding environment in which the sound has to travel. Okay, you are increasing the temperature of the gas in which the sound is traveling. Okay, so when you will increase the temperature of the gas, the gaseous molecules will have more energy and they will spread far apart. So the density will drop. Okay, so the density of the gas will drop. Now if you can see, density and velocity, they are inversely related. So if density is dropping, the velocity will increase. Okay, so now can I say that if we increase the temperature of the gas in which the sound is traveling, the velocity will increase? Yes. Okay, so I have explained it conceptually also. If you increase the temperature of a gas, the density of gas drops. Okay, now when the density of gas drops, it is inversely related to the velocity of the sound in that gas. So the velocity of sound increases. So effectively what I can say is, if the temperature of the gas increases, the density of the gas will drop. Therefore, the velocity of sound will increase. Okay? This is the relationship that has been explained conceptually. Now, you also have the second factor that is now to be looked at, P, which is the pressure of the gas. Now, although pressure term appears in the formula, but the pressure of a gas is really not going to affect the velocity of the sound wave in the gas. I'll tell you why. You see, V is equal to under root gamma P by D. Now this D, I can write, this D is nothing but the density. So density can be written as mass upon volume. Okay, we all know that. So this formula effectively becomes gamma PV upon M, because this V, as you can see, it is in the denominator of the denominator, so it goes up PV. Now in chemistry, PV, the product of pressure and volume for any enclosed gas, according to Boyle's law, if you remember, PV is equal to constant. So what is going to happen is, now let me write first this formula clearly, gamma PV upon M. Now, supposing somebody is increasing the pressure of the gas. Okay, have a very careful look. Somebody is increasing the pressure of the gas. Now, according to Boyle's law, the product of P and V has to be constant. So for it to be constant, if somebody is increasing the pressure, the volume has to come down. Okay, so that this increasing effect is neutralized by this decreasing effect. So effectively the product of P and V is not going to change. That is why the velocity of the sound in that gaseous medium is not going to change. Okay, so now what you understand is the dependence of density, the dependence of velocity of sound on the density of the gas as well as the pressure of the gas. Pressure of the gas does not have any effect on the velocity of sound, whereas the density of the gas actually really has an effect. If density decreases, the velocity of the sound increases. Okay? Okay students, so let us move on to some more formulae. Now by the end of all this, you will have a better understanding of where to apply which particular formula. Now you see, we have already discussed two formulae. Now this is the third one. You will easily understand where which one is applicable. Now you see, this is V, and in small on the right hand side you have T degrees centigrade. Okay, so this means velocity of sound at a given temperature T degrees centigrade is equal to velocity of sound at 0 degrees centigrade plus 0.61 times T. Now what does this formula tell you exactly? Now you see, this is a formula telling you the dependency of the velocity of sound on temperature, where in a gaseous medium. Okay, so whenever sound is traveling in a gaseous medium, just now we have already discussed that if you increase the temperature, of the gaseous medium, we just now discussed that the density of that medium, gaseous medium, will fall. Therefore, the velocity of the sound wave will increase. So effectively, if you see the relationship between temperature and the velocity of sound, temperature of the medium and the velocity of the sound, they are directly related. If you are going to increase the temperature of the gaseous medium in which the sound is traveling, then the velocity of that sound wave will also increase. More the temperature of the gas, greater the speed of sound in that gas. Okay, so now this conceptual understanding now has been put across in terms of a formula. So here you can directly relate. Now this was only concept. This is actual quantitative analysis in which you can actually get the values. Okay, now suppose by experiments we have found out that velocity of sound in a gaseous medium at around 0 degrees centigrade is roughly 320 meters per second. Okay, so given this particular value, if somebody wants to find out the velocity of sound wave in a gas at 15 degrees now, in that same air medium or the gaseous medium, now the temperature has been increased from 0 degrees to 15 degrees centigrade. What will be the new velocity now? So conceptually we all understand that the temperature has been increased. See, earlier it was 0, the velocity was 320. Now the temperature has been increased from 0 to 15. So there should be an increase in the velocity also. Conceptually we understand that. But numerically and quantitatively, what exactly will be the value of velocity of sound at 15 degrees, that we can get from this particular formula. So let us use this, let us try to find the solution. V at 15 degrees centigrade, I am using the formula, equal to V at 0 is already given as 320 meter per second plus 0.61 multiplied by T. T here is nothing but the change or the increase from 0 to 15. So that is an increase of 15 degrees. Okay, so if you calculate this, you will get 320 plus 15 ones are 15, carry 1, 15, 6 are 90 and 91. Two places of decimal, so I am going to put the decimal over here. So you are going to get 329.15 meters per second. This is the velocity of sound in that same air medium or the gaseous medium at 15 degrees. So now if you compare the values 320 and 329, obviously there is an increase in the velocity of sound. Why? Because there was an increase in temperature. Okay, so this formula is particularly for gaseous medium when there is a change in temperature only. Okay, now coming to by the way, this is a part that I had mentioned, I had forgotten earlier. Sound is also a kind of a wave, just like light wave. So just like light wave undergoes reflection, refraction, absorption at different surfaces, similarly sound can also, if you speak in front of a cliff or in front of a wall or something, your sound that gets generated, it will strike the surface and it will reflect. Similarly, while going from one medium to another, it can refract, that is bend also, it can be absorbed by a surface, and so on and so forth. Now coming down to the next formula that we have, V is equal to under root T by M. Okay, now let's see, again this is a different formula. So what is the case in which it will be applicable? This will be applicable in case of velocity of transverse waves produced in a stretched string. Okay, so this is a stretched string, suppose for example a dhaga, or maybe you can say for example a rubber band, elastic rubber band or something. Okay, so it is stretched at two corners. Okay, suppose this is one end A, this is another end B, and this is a stretched string. Now if somebody comes and disturbs, you pluck the thing over here, so what will you see? You will see that there will be a disturbance created in this particular, either in this particular form or in this particular form, things like that. So basically what you understand from this disturbance is that this is a sound wave that is getting generated. This is not a longitudinal waveform, but it is a transverse waveform. And where is it getting generated? It is getting generated in a stretched string. Okay, so what are the varying factors? Now you can stretch the same string. Earlier you had stretched it between A and B. You can stretch the same piece of string to a greater length, okay, PQ. So that means in this particular case of stretching of the same string, tension T is more. Okay, here T means tension. Okay, tension in the string. As you can see, T is equal to tension in the string, and in the formula you see tension is right at the top. That means T and V, they are directly related. That means if you are stretching the string more, you are creating more tension in that string. So when it will get disturbed, the velocity of the sound wave that will be created will also be more. So more the tension in the string, more will be the velocity of the wave produced. Now coming to this particular factor M, which is the mass per unit length of the string. That basically means how much mass is concentrated in that piece of string that you have. Have you taken a very thin string or you have taken a thick string? Suppose you take a thick string means more mass. Okay, now if you have mass value more, you see mass and velocity, they are inversely related. That means if you take a thicker string, mass will be more, velocity will drop. Okay, so in case of a thicker string which is stretched, the velocity of the sound wave created will be less. But if you take a very thin or fine piece of string, that means the mass will be less. So if the mass is less, the velocity will be more. Okay, so this is what I basically wanted to help you all understand. There you will find in the book also there are these different formulae that are given. You must understand that they are all for different scenarios, in case of different mediums, different bodies, different factors that are changing. Okay, so you must be able to understand and apply the right ones in the situations. Okay, so we'll end up over here as far as the first lecture is concerned. The next topic or the next lecture in this particular chapter will be the formation of the echoes. Okay, echo is a formula in which the sound gets reflected from an obstacle and you hear the originally created sound as well as the reflected sound after a small gap. Okay, so that particular sound is known as the echo. The details and the formula and the numericals will be studying in the next lecture. Thank you, children.